So suppose I want to find the area enclosed by this polar curve. I think the first thing I'm going to do is just show you a formula for this, and so I'll just talk in general terms, and then afterwards we'll find the area of this whole thing. So the idea is we want to find all of that area, but we have a polar curve, not just a regular curve. So let's talk in general terms. So instead of thinking about this, we're just going to have some R equation. I'll do it in blue. So it's not always going to be the same, of course. We're going to say that it's f of theta, some function involving theta. That's what that means. And I want to find the area of this. Now, normally, if we had a regular curve, we would think about splitting it up into small rectangles and then adding those up, and we add an infinite number of those up, and it becomes a definite integral. Same idea here, except for instead of rectangles, we're going to use sectors. So I would have these infinitely small sectors that I'm going to add up all together. So let's think about that. If I want to figure out the area of a sector, I'll draw a sector. That's like part of a circle. That's what we're going to think of, where this angle would be, let's call it alpha. If that was alpha, and I had part of a circle, well, the area for a whole circle would be pi r squared. Yes? Well, in this case, we don't have the entire circle. We have, well, actually, let me call this theta. It'd be better if I called it theta. So we don't have the actual entire circle. How much of the circle do we have? Well, the whole entire circle would be 2 pi radians. So if I multiply this by theta over 2 pi, this is like the percent that I have of the circle, the fraction, because I only have theta of this whole 2 pi. This is like 100% of the circle. This is what I actually have. So I'm multiplying it by that fraction. And that would be the area of the sector. Yes? Let me rearrange that. The pi's would cancel out. So that's what we would have, 1/2 r squared times theta, times our angle. Well, how can we write that with our picture here? So that's the area of the sector. And I'm making a really, really tiny sector here, where I have, I mean, it's not like a circle, but when it gets really, really small, we can think of it as a circle. This angle, that angle is going to be d theta, a really, really, really tiny, tiny theta, really tiny angle. And the radius, well, that's r right there. However, remember, r is some function of theta. So this r is f of theta. And if I'm finding the area of that, it's simply 1/2. So the area of that sector would be 1/2 times the radius, f of theta, but I have to square it. So the radius squared times our angle, theta, except for that angle here is d theta, because it's really, 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 really tiny. D theta. I don't know why I was going to divide it. So that's the area of the sector, but if I want to have an infinite number of these and I want to add them all up, I just take the integral. And I do it from some alpha to some beta, which means my starting angle and my ending angle, which maybe we'll find an area of a sector of this, or like of a piece of this. That'll be more interesting. So this is the formula, the area formula for polar curves. This is super, super nice because we're given what r is most of the time. That's how polar curves are defined, with an r value. So there you go. This is the formula that we're going to be using. So actually, in the next video, we'll take a look at finding the area for a piece of this. That way it's a little bit more interesting. So there you go. That's the formula area for polar curves. Hopefully that makes sense. And we're going to use that in the next video.